after you jot the heading down from Edline, this is the first thing that should come up as your notes. So that's kind of how the structure is going to work for Chapter 7, like we had talked about, where you're going to have a PDF document of the heading that you're going to jot down from Edline each day, and in the video we'll just proceed from there, because it seems to be almost a waste of time to put the heading up when it's provided right here. So again, excuse me, I am sick, so if I sound very nasally more than usual, just excuse that. Okay, so let's look at part A. We talk about using the x-intercepts to graph polynomial functions. So to summarize polynomial functions thus far, this is the structure we have. So I advise you to pause the page and go ahead and try to jot all of this down. I don't expect you to do it as I'm talking, so just jot it down and then you can go from there. So if you look at the function we're given there, that's the very specific notation, that's the technical notation like we talked about in class, is given to be a polynomial. So zeros or the k is a 0 of f of x. We've talked about that, where we're using the letter k. K is not anything more than referring to that as a potential constant. Factor is saying x minus k, so when we said if k is 10, then it would be x minus 10, but if k is negative 3, it's going to be x plus 3. So it's kind of how that factor is looked, but we're saying that x minus k is a factor of f of x. K is a solution of f of x, which equals 0, which you kind of see how the solution in zeros, as well as the x-intercept, which is a 0, and the x-intercept of f of x. So they correlate with one another. So if you look at the 3, factors is a technical way to write that in factored form, but 0 solution and x-intercept in this sense are all considered to be the same thing. Okay. So if we look, when given a polynomial function, there are a few things we need to consider. There's 4 things specifically, and we're going to try it out. So the first one being the factor the polynomial completely. We've talked about that many times, how factoring completely is very essential. In this case, it absolutely is. Most of the time, you'll get one that already is factored. Not every time. One example we will do is not. And you want to identify zeros where the real zeros are the x-intercepts, which we talked about that previously, how the zeros, solutions, and x-intercepts all tend to be, or not tend to be, they are the exact same thing. Create a table with x values beyond and in between the real zeros. So that's another thing that's a little bit new, but if you say you get 4 zeros, say the zeros are 0, negative 2, negative 4, negative 6, you want to pick numbers that are just outside the negative 6 and positive 2, and then pick from there what values are in between. It does not matter. Not everybody's table is going to be the exact same, but the graph should look almost the exact same, because there is one way to graph it, but by hand the sketch is going to be a little bit off. And then lastly, we want to determine the function's end behavior. We talked about that. I'm not sure why that E is not capitalized anyway. But that's something we had talked about before. We're going to get back into it. And you don't even actually need to know what it looks like we had talked about before, because you know what the end behavior is going to be. Knowing what a simple linear, a negative slope linear, a positive quadratic, or a negative quadratic, depending on what those leading terms are. Okay, so let's take a look at the first example. First example being f of x is equal to negative 2 times the difference of x squared and 9 squared. Correction, it's actually f of x is equal to negative 2 times the difference of x squared and 9 times x plus 4. It's not to the second, not that x squared minus 9 is not to the second power, it's to the first power. Okay, so let's consider what we got to look at first. So automatically we can tell on appearance that it's not factored completely. Very quickly, if we talk about doing that, you realize that that's the difference of squares, x squared minus 9 being x minus 3x plus 3. Okay, so we can get some zeros from there. Knowing that negative 2 is practically irrelevant in terms of finding our zeros, we can see that if we identify them, it's going to be negative 4 from the farthest binomial, negative 3 from the middle one, and then 3 from the first factor there. So if you look at those 3 binomials that are factors of the original polynomial, those are the 3 zeros we come up with. Well, knowing that, we need to create a table of x values and beyond, or that are beyond and in between the real zeros. So if you think about it, we're looking at negative 4 as the extreme to the negative values of x, positive 3 extremes the positive values of x. So we want to think of something, maybe negative 5, maybe positive 5. That's to decide what I picked, and I already wrote it all out, but it's something you could double check if necessary. That it's going to be negative 5, which the y value is 32. So you can do synthetic substitution. You could do direct substitution depending. You can see that these values here are going to be zeros, which is a given. And then if you look at the extremes here, the negative 5 and the positive 5, those are values that are really hard to graph. So you can see why it's very effective to find values that might be a little closer. So we probably could have picked positive 4 or 3.5 or something that's not going to give us something that outrageous. Okay, so take a second and jot all this down because we're going to move to the next slide. If you look then, if we're going to graph the function, this is a picture I had taken after I had graphed it myself. And you can see these are very hard to tell where these are, but those are all the points we had picked, and you can see the 2 intercepts being right there and right there, and the third one being there. And you can see that this is another solution to this entire thing, which we'll just leave it out for the time being. Not relevant in terms of the way this is depicted. So the three solutions we're really considering are those, and then there might be some other things we can look at later on. So if we look, we want to determine the function's end behavior. We have a function that f of x approaches positive infinity as x approaches negative infinity. So as the value moves to the left, so the x value moves to the left, it gets much greater. As you can see, when it's around 6 to x value 6 or negative 6, negative 7, it's upwards of 100 to 200. And as we saw, when the function goes to negative infinity, is the x values go to positive infinity, because we realized when we plugged in x or 5 for x, we got negative 288 as the output for our y value. So that was something that was way below what's obviously depicted there. Okay, so there's one other thing we want to talk about. Consider the following graphs and answer a couple things. It's kind of a warm-up. So let's talk at three things: type of function, polynomial degree, and the number of direction changes. Okay, number of direction change is something a little different. We're going to talk about what that means. But I picked really three very easy functions to look at, to consider. Okay, so let's take the first one. The first one is a line goes through the origin. That's y equals x. Very simple. So if we link what would be the type of function, polynomial degree, number of direction changes. So type of function means it's linear. We know that the polynomial has a degree of 1, and the number of direction changes is something that's new. But in this case, we can see that there is no direction changes. It continues in one direction forever, or the other direction forever. It never does change its direction. Now let's look at a quadratic function. This is y equals x squared, positive x squared. So we can say, okay, again, it's quadratic, degree being 2, because it is a quadratic, which we know the leading terms to the second power. And the direction is as x approaches 0 here, it changes when it turns to positive values. When we're looking at the positive values first, when it gets to 0, it changes its direction. So in that case, there's one direction change. If we look at the last function, this is a cubic function. So the degree we know has to be the third power leading coefficient's term, or the variable leading coefficient is 3. And then we know the direction change, there's going to be 2. So as it approaches here, it kind of flat lines at the origin, and then again changes directions here. So the direction changes before it reaches the origin and after the origin, not at the origin like the quadratic does. There are two direction changes. This is very relevant because if we look at the next slide, I'm going to show you, you can see that there's a definition for that. So the turning points are what those are called on polynomial functions. The graph of every polynomial function of degree n has at most n minus 1 turning points. Thus, if f of x has n distinct real zeros, then the graph is exactly n minus 1 turning points. So if we go back a second, we go think, oh, linear term. Degree is 1. It means n minus 1 or 0 change directions. Degree is 2. N minus 1, 2 minus 1 direction changes, or turning points. That's how many turning points there are. And degree 3, 3 minus 2, or I'm sorry, 3 minus 1 is 2, which gives us 2 direction changes or turning points. So again, that makes a lot of sense now looking at a formal definition. It's a lot of very wordy. That's in a nutshell what it's saying. There's one less turning point than the degree of the polynomial. So one more thing to note here, and which is what we're going to pick up with in class. I have an example in a handout we'll look at. The turning point at the highest point is called the local maximum of the nearby points, and the turning point at the lowest point is called the local minimum of the nearby points. When I say lowest point in this sense here, and highest point, I'm referring solely to the function's highest point at that point. So if we go back to a couple examples, we can see that when it crossed the origin, that was the local max, or local min, and then when it reached a little bit past the y-axis, it's somewhere around 60 to 70, that's the local maximum at that point. Okay, so there's something we're going to look at in class. Just want to give us a little bit of introduction. About 9 minutes, not too bad. Best of luck. Make sure you go back so you can get everything down. Make sure you have everything ready to go for the next day. Okay, thanks guys. Have a good one.